This is Jack Creel, and I'm going to be running through my problem solutions for week 4. So the first problem is asking us to find the temperature at the base and the heat loss through some flanges where the flanges are connecting these circular sections of pipe. And so we're going to start by assuming steady state, one-dimensional, the properties are constant, things like thermal conductivity, mu, rho, etc., and that the radiation is negligible. So we start by finding our conductive and convective resistances with the equations we know from our notes from class. We need the outer area for the convective resistance. And once we find both of those, we can sum them and put them under the overall temperature gradient to find the overall heat transfer rate given here. And then using that, we can look at just a part of our system. So I'm just looking at the convective part to find the temperature at the outer part of the pipe wall, which is the temperature at the base of the flange, which is about 150 degrees Celsius. And next, we need to find our fin efficiency. So we're going to do that using squiggle as well as this ratio here. So we go through and find each part of squiggle, not too hard. And once we have the overall squiggle as well as this ratio here, we can use them both through figure 3-44 to find the overall fin efficiency. Once we have that efficiency, we know we can use it in this equation to find the overall heat transfer through those flanges. And once we plug everything in, we'll find that about 16.3 watts are lost as heat through the flanges. The next problem wants us to find the heat transfer rate and plot the temperature profile for these circular fins under a few different boundary conditions. The first one being an infinitely long fin. So we're going to go through each part here and just use the heat transfer equation for that boundary condition. So we have this one for an infinitely long fin from our notes. You can find that heat transfer using it. I went through and found M here because we're going to use that number a lot. So I just wanted to get that out of the way. And we also have the temperature or the equation for the temperature profile for an infinitely long fin from class. So what's essentially going to happen in each part here is we're just going to modify these equations to fit the boundary condition. So now our boundary condition is an adiabatic tip. So we have this equation for heat transfer from our notes. So we just adjust that, find the new heat transfer, adjust the temperature profile equation, and then we're going to put our temperature profile equation into Excel with increments of x to find the temperature profile. So that's what we did. We adjusted both equations and found our new values. We're going to do the same thing here for specified temperature at the tip now. So change this equation, find the new value, change this equation, go into Excel, find the new profile. Same thing here. Now we're doing convection through the tip of the fin. So new equation here, new value here, new equation here, new temperature profile found in Excel. So here are all the temperature profiles. You can see how those boundary conditions are going to affect these things. And so we would just be putting our temperature profile equations right in here in terms of x. The last problem is about a circuit board. It wants us to find the temperatures on both sides of the circuit board. In part A, it's just the circuit board. Part B, they add a sort of fin system. They epoxy it on one side. So for the first part, we are going to go through and find our resistances as we're used to. Nothing new there. Gonna sum them, put them under the temperature gradient. This time we already know the heat transfer rate, so we're actually going to use that, rearrange this to find the temperature one on one side of the circuit board, go through it with just a part of our system here to find the temperature at the other one. Now for part B, it becomes a little more complex because we have this fin system. So we're going to start by finding squiggle again to use with our figures to find the overall efficiency of the fin. Once we have that, we can write our heat transfer through the fin equation here. I've also written our heat transfer for the unfinned portion here. And we know that the sum of those two are going to have to equal our total heat transfer rate, which is given in the problem statement. So I can write that out mathematically here, rearrange this for TB, and plug everything in. And I can find that. And then the next step is going to be to go through and find our new resistances for this equation, or not for this system, our new system here. Go through and find the resistances for all of them. One of the resistances is still the same, so we grab that from above. And then we're going to go through and find the temperatures that we need at each part in our system from up here. The two temperatures on either side of the circuit board, using the same equation here.